All right. So let's take a look at this mechanism. We have this interesting looking starting material, cesium fluoride. First off, cesium fluoride is ionic. We can show this as cesium plus. Cesium is underneath sodium and potassium, and F minus. Two lone pairs. Cesium plus, F minus, ionic, not covalent. The instructions say using appropriate arrows to show all electron movement, provide a detailed stepwise mechanism, show complete Lewis structure of all products. A number of folks did not show complete Lewis structures. Many folks did not do that. The mechanism begins with the fluoride anion, there it is right there, acting as a nucleophile, and the oxygen on the silicon acting as a leaving group. Okay, let's take a look at where we're going. First off, Lewis structures. CF2, that's a carbene. That's carbon with two F's bonded to it. It's neutral. I should have put that up there. Carbenes are neutral. There's one lone pair there. And if you could do formal charge, that carbon is neutral. In organic 1, I showed like a plus and a minus charge on this. Net neutral. This is just a silicon, which is below carbon in the periodic table, so it makes 4 bonds. It's bonded to an F. Of course, these has lone pairs. I'm not putting all the lone pairs there. And then 3 methyls. CH3, CH3, CH3. CO2, carbon with 2 bonds, double bonded to oxygen, of course, lone pairs. SO2, very similar, but sulfur is going to have a lone pair. Because if you just double bond it, you'll see that sulfur only has 4 electrons that it's owning. There's also a lone pair. SO2 is neutral. Now the sulfur is neutral. And it's bent, stuff like this. Okay. We've got to see where we're trying to make here. We want a fluorine bond to the silicon. It tells you in the instructions that's the first thing you're going to do. Important arrow movement. Every time you move arrows, you want to start by saying what?
These arrows.
These electrons. You've got to identify the electrons you're moving. These electrons, I'll circle them. We're going to add to the silicon. Now from here you can do 2 different ways. Most people that got this right did a pretty good job. Just kick this oxygen off. There's no longer an oxygen there. What does this arrow movement give? Now this arrow movement can be more precise. Let's move these electrons onto the oxygen. There's 2 lone pairs there. We're going to move this bonding pair onto oxygen. This fragment is going to be this 2 F's, oxygen, 2 lone pairs. What does this arrow mean? F is making a bond to silicon. Let's draw that. But really that's there. So we're going to make that, yeah? F bonding to the silicon. Okay? There's that. What does this arrow mean? Bonding pair moving on to oxygen as a 3rd lone pair. That's it. Now this is a minus. Cesium is just a spectator ion. In fact, we have to reform cesium fluoride over here. Okay, let's work with this here. We've got this. Next, I see CO2. And right there I kind of see CO2. Carbon here. Now we said this in class already, but when you were doing this mechanism, maybe we hadn't said it yet. But anytime you can make a lone pair and kick off a leaving group, that's going to be something easy to do. Right here, these electrons can move in, make a pi bond, and kick this off. we do have to make carbon double bonded to two O's. Right here is doing that. What does this arrow movement give? We now have, I'll draw in the C, double bond. I'm going to draw it linear instead of bent because it is linear. That right there is now carbon double bonded to two O's. There's your CO2. This arrow, these electrons break away from the carbon and move on to this carbon as a lone pair. That's going to give F. This carbon has an F on it, an F on it. What else is now on this carbon? Right there. These electrons move on to this carbon as a lone pair. That is a minus charge for that carbon. Neutral molecule formed. Neutral molecule formed. We formed two of these. We formed that. We formed that. We've got to form these two now. By the way, let's go back up here. There is an alternative way to show this. Because when this oxygen left, you may say, well, that oxygen is not a good leaving group. Shouldn't we have to protonate it? It doesn't have a positive charge. Before we did anything, we could have actually shown a resonance structure where these electrons went here and these went up, and we could have gotten just this, these electrons here and these up. This is a resonance structure of this. And if you do a resonance structure first, you can see that that oxygen does have some partial positive charge on it. And so then you could maybe feel a little bit more comfortable in this attacking and kicking off that positive charge. Okay, there is some partial positive there. Let me show you another consideration though. There's another way to do that. We could have also done this. We could have also just added the F minus to the silicon and not broken that bond. We could have formed a species that looked like methyl, methyl, methyl. We could just have an F bond in there, where just the F just bonds, nothing leaves. Why? That silicon has 5 bonds. Carbon can't make 5 bonds. But silicon, having d orbitals, can make 5 bonds. So this is actually reasonable. Now the silicon here would have a minus charge. And if we just added that silicon fluorine to the silicon, we just did an addition. And after you do the addition, then you could do the elimination or ionization. At this point, the silicon would like to become neutral. It can get back to neutral by this leaving group just leaving. And if it left, what would you get? Well, you would get this, and you would form that right there. So there's 2 different ways to do that early on still. From here, though, we can make pi bond, form CO2, kick that off, lone pair here. Now, at this point, we got to get rid of this sulfur. There's a lone pair there, lone pair there. At this point, this carbon doesn't like being minus. This thing can just leave. And that would give us sulfur What does this arrow mean? WDAM. What does arrow mean? What does this arrow mean here? The electrons are breaking away from the carbon, moving onto the sulfur as what?
Lone pair.
A lone pair. So it's got a lone pair and an F. What are we left here when that breaks away? We're left with that. A carbon with a lone pair and two fluorines. And that's now a neutral carbon. And that's what a carbene is. Why would this leave? Well, the carbon gets to go back to being neutral. Now, carbenes don't have an octet. They're a special type of carbon bonding arrangement. Now we're down to this. We formed those. How are we going to form SO2? What needs to happen here to get SO2? Which is, if you drew Lewis structure, two double bonds to oxygen and one lone pair. What do we need to do for this to become just neutral? By the way, we're missing something here. Because when this happened, we formed this and that. Both of those are neutral, but this was minus. Something has to be minus. What's minus? Sulfur's minus right here. Because the sulfur owns 1, 2, 3, 4, 5, 6, 7 electrons. It's only supposed to own 6. It's in group 6. It's a minus. So at this point, the sulfur wants to go neutral. How can it become neutral, and how can you get to the final products?
Taking off the F, taking off the full.
Yes. Now let's use an arrow incorrectly. I'm going to take these electrons or something and do an arrow like this. Well, let's show what that would give. This gives something that's not good. That arrow movement would give a sulfur with a lone pair, double bonded to oxygen, double bonded to oxygen. What does this mean? 2 electrons moving on to sulfur as another lone pair? Well, now the sulfur has 2 lone pairs, and that's a 2 minus charge. But SO2 is neutral. We don't want these electrons to go into the sulfur. By the way, if it did, what would the F be? It would give that plus F plus. No, that's not good. What do we need to reform in this reaction at the very end?
CS F.
F minus needs to reform. F minus is the catalyst. It needs to reform. We don't want to do that. We want these electrons to leave the sulfur, move on to the fluorine as the 4th lone pair, and we need to get a sulfur double bond to O with just 1 lone pair. But that's actually a neutral sulfur if you can do charge. There it is. So boom, we made that. What are we making right here? F with not 3 lone pairs, but these electrons move on to the fluorine as the 4th lone pair. That's minus. And we have reformed our catalyst, which is the definition of a catalyst. The cesium is watching all this. The cesium is the spectator ion. It's still there. I mean, there's cesium fluoride. You can show it like that, or you can show it like this, however you want to show it. It's ionic. Now for you guys here with me, how do we do? Questions? Questions about this?
Makes sense when you do it. Or it makes sense after that class period that we actually went over this stuff. One question that I did have though is, how do you know if it's a spectator ion?
What else are you going to do with cesium?
I mean, there's nothing I can think to do.
No, we're never going to use cations, sodium, potassium, cesium, magnesium. Never. I mean, you got to know that it involved with a mechanism. Have we ever done a mechanism that involved like a group 1 metal cation? No. And a lot of times in class, if something like this is shown, I'll say, okay, this is F minus, right?
Right.
Or if we have sodium hydroxide, I'll say, okay, let's get rid of that, this is hydroxide. That sodium, potassium, lithium, they're just going to be the cations, the spectators.
Okay.
They're not going to do anything.
Also, how does, in the third or fourth step, how does the lone pair on the carbon with the two F's go across the sigma bond straight to the sulfur?
Do one down here?
One down, right there.
Mm-hmm.
How does that lone pair go across that sigma bond and just go straight to the sulfur?
No, this lone pair is not doing anything. These two electrons in the bond
Oh, okay.
are breaking away.
Okay.
Here's the bond. These two electrons just break and break away from the carbon, just move on to the sulfur as a lone pair. The lone pair on that carbon is still there.
Okay, let's see.
And what drives this? Well, the carbon gets to go back to neutral. Even though it doesn't have an octet, it gets to go back to neutral. By the way, you have to do that because you have to get rid of the sulfur. Sulfur becomes minus, but what type of stability? First off, this is driven by entropy. One molecule becoming two. Does this have any stability? Yeah. Sulfur is electronegative compared to, carbon or... also, you have dipoles here. Oxygen's pulling, F pulling. That sulfur is very stabilized. But still, the sulfur would like to become neutral, and it can become neutral by the F saying, okay, guess what, sulfur, I'm just going to leave. You're not going to care because you're going to become neutral, and I get to become minus. And F is the most electron greedy on the periodic table. And of course, this gets you where you need to go. Hope that helped, guys.